morning, friends. We were continuing our effort to understand how to compute how much fuel is consumed during cruise or maybe during loiter. And in that process, we have seen, depending upon type of aircraft you are using, that is precisely what is the engine being used. If it is jet-driven engine, then we have seen R can be expressed as V by C, L by D to ln Wi minus 1 by Wi. And for endurance, it is L by D divided by C into ln Wi minus 1 by Wi. Similarly, for propeller-driven engine, here we know that R is neta by C, L by D, ln Wi minus 1 by Wi. Similarly, endurance is neta by C, L by D, 1 by V infinity into ln Wi minus 1 by Wi. This we have derived, right? And what we are looking for, let's say we are talking about jet engine driven aircraft, and I am moving from point 1 to point 2, which is, let's say, cruise at a certain speed. Then for fuel consumption, if I use this first expression, I need to know what is the R, what is the V with which I am cruising, what is the value of C, and what is the value of L by D. If I know these values, then can I easily write Wi by Wi minus 1, which is nothing but W2 by W1. If I refer to this diagram, that will be equal to exponential minus R into C by V L by D. This is directly coming from here, right? So if I really want to know W2 by W1, means during this phase how much fuel has been consumed, I need to know the value of R, that is how much range I want to fly. And it is a jet-driven engine, what is thrust-specific fuel consumption for type of engine. And do not forget, these are all initial sizing problem we are handling. Some approximation will be there. Mostly they are based on historical data. V, you know at what speed I am going to cruise, and the major question also comes at what L by D should I fly. As far as L by D is concerned, we will be discussing a little later. We have already built up our background for selecting L by D. Let us focus on C, that is thrust specific fuel consumption. Let us revisit what is the definition of thrust-specific fuel consumption. And if you recall, it is for jet, we define it as weight of fuel consumed per unit thrust per unit time. So typically, if you see, CT is rate of fuel consumed per unit thrust. And if you see, most of the handouts given or most of the design charts available, they are all in FPS unit or sometimes inconsistent unit. If you read earlier books, even recent books also, the units will be in FPS. There are many attempts to convert into SI units, but you can understand all those tools, jigs and fixture which are already made, they have been made based on FPS system. So there is a resistance in converting to SI units, but things are improving. Since most of the books they are talking about all those calibration, all those correlations through FPS unit, I will also use FPS unit with lot of word of caution so that you can correctly use it. You will find that most of the books see they have expressed in a unit pound of fuel per hour per pound of fuel, right? So this is rate of fuel being consumed and per unit thrust, which is in pounds. And if I expand it, you will find this will be, unit will be given in terms of 1 by hour. For example, you will find the values of C for such cases may be given as 0.5 per hour. But when you want to use this formula, here we have to be consistent in unit. So my examples are with FPS unit. So C, I should convert it into per second. This is very important, and you will see while I solve example, I will be using that. This is one observation. Second observation is that although we will be giving example using an aircraft driven by jet engine, but we should also know how to handle if it is a propeller-driven engine. In that case, how do I handle this C, the specific fuel consumption? So I thought I must mention at this point how to handle that. Before I come to that, as I have been telling, what is the value of C? Typically, I wrote around 0.5 or 0.6 for cruise, some historical based number, to ensure that we can pick those numbers depending upon type of engine you are using. You can refer one chart which I will be showing it to you. Typically that gives value of CT versus Mach number for different type of engine. You can refer the figure there, and for different combination of engine, different type of airplane, a type of Mach number you are flying, you can pick the value of CT based on historical data. But when I say, I repeat again, these are all initial preliminary sizing. So these are some guideline number. Finally, anyway, we have to modify this, improve this, right? Now coming back to the propeller part, most of the book will be using some notation, and I will be also following those notations. And let us see, for propeller, we use something CBHP. This is defined as pound of fuel per hour to produce 1 horsepower at the propeller shaft. This is important, at the propeller shaft. After combustion, what is the power available at the shaft? And that is what we are talking about, propeller shaft. And you know that the power is available at the propeller shaft How much you can extract, that depends upon what sort of propeller you have put and what is the efficiency, right? So now the question comes, how do I get a feel from this power available and from the extraction of power? I want to know how much thrust it will be generating. That gives us a better understanding of design to fix initial numbers. So there will be a similarity in interpretation between CT and CBHP via how much thrust it will produce. Okay? So we will be doing that now, because most of the books are doing that. What is the physics behind it? We write the engine produces, this is important, thrust via propeller, no problem, which has efficiency NP. And exactly I was telling, what is the power available at shaft, what is the propeller efficiency, that will decide how much it has been extracted. And we are now telling the engine produces thrust via propeller which has efficiency NP. This is the question we are going to address, so that I have a similarity in my understanding between CT and CBHP. Right. So if I do that, then I write C is weight of fuel per unit time by thrust. That is what, in fact, CT, that is the thrust specific fuel consumption. And now also we know CBHP is again rate of fuel, but per horsepower, per unit horsepower. This is the two different ways of defining CT, which is thrust specific fuel consumption, and this is we call specific fuel consumption for propeller-driven airplane. And we are trying to look for how to see CT and CBHP are related, or we want to know how much thrust this gentleman propeller-driven will generate for a given condition for a typical value of CBHP. Now if I use this CT, I write it as CBHP. Let me write this so that there are no issues. We are trying to find out how do I visualize what is the thrust I expect for an aircraft which has particular value of CBHP. In turn, I am looking for a relationship between CT and CBHP. Okay? So we go back to definition. CBHP is pound of fuel per hour to produce 1 horsepower at propeller shaft, and we know that this is linked with the power available at the propeller shaft. Depending upon what type of propeller efficient you are putting here, installing here, you will get the power available, okay, which will be used for giving a thrust to the airplane. So that is what is written here. The engine produces thrust via propeller which has efficiency neta P. Now if you see the definition of neta P, if you come here, so neta P is defined as thrust power output divided by horsepower input, because this is the horsepower being available at the brake, and finally what is the thrust power output you are getting, which is making the airplane to move. So if I write now a little more here, I know thrust power output is nothing but thrust into V, the speed at which the airplane is moving. And what was horsepower input? That was horsepower, HP at the brake, but to be consistent in unit, I have to multiply 550 because I know the relationship of converting horsepower into the FPS power unit. Okay. So once I know what is NP, by using this equation, I can write thrust equal to 550 into NP into HP divided by V. No issues. Now come back, what is our aim? I want to build a relationship between CT and CBHP. So I start from here, CT is WF by time, that is rate of fuel consumed, divided by thrust, and for WF by time I use this equation. So CBHP into NP, this term, of course I write CT here. Now for thrust I use this expression for thrust. So I get CBHP NP into V by 550 NP HP. NP gets cancelled. So finally you get a relationship CT equal to CBHP V by 550 1 by NP, which is propeller efficiency. So this will tell you how much thrust is being extracted once propeller or engine is rated through power. And what is that meaning? Again, designers input to us that if NP is 0.8, 1 horsepower you can visualize equivalent to 1 pound of thrust at 450 feet per second. This is extremely important when you are designing an airplane, that you have feel for number. 1 horsepower means 1 pound of thrust at speed 450 feet per second. But you could also see that this relationship demands the value of V, neta P, and CT and CBHP are also function of what sort of setting you have got in the engine. But as I am repeatedly telling, so far the exercise is to get an approximate or number so that I can start configuring the airplane, which is my preliminary configuration design. Okay. So I thought this should be made clear to you before we go for further application. If you have any problem in this part, do write in the forum, because as a designer you need to understand these things very clearly and develop a feel. Typical values I am giving, typical values for jet engine aircraft, pure turbojet, for cruise and for loiter. If I show here the value of 0.9, it is around 0.8. And for low bypass turbofan, mostly we will be using turbofan in our example. Maybe you may pick high bypass ratio. This value is around 0.8 for cruise and 0.7 for loiter. And for high bypass ratio engine, this value is around 0.5, and for loiter it is 0.4. These are all typical numbers, right, for jet engine. Now when you come to propeller-driven engine, then the values are for propeller, C is equal to C, BHP into V by 550 neta P. Say if I give the values of C, BHP, and next value is neta P, because you understand that when I am trying to get the meaning of CT via CBHP, this will change for different value of propeller efficiency. That is why these values are given in this fashion. Say for a piston prop, like fixed pitch propeller, this value will be for cruise, this is 0.4, and neta P is 0.8, and for loiter it is 0.5, and 0.7 you should take as NP, neta P. So this is top one numerator is CBHP value and denominator is neta P value. It is required because we have seen that CT and CBHP are related through neta P. Similarly, for piston prop, but variable pitch, this value will be 0.4 by 0.8 and 0.5 by 0.8. That is, the value of CBHP will be 0.5 and neta P is for 0.8. For turboprop, which is very popular, turboprop, this value is 0.5 by 0.8, and here it is 0.6 and neta P is 0.8. These are typical numbers, right? L means loiter, now you are expert, and C means cruise. So this is a guideline to select the values of C, BHP or CT depending upon type of engine you are using. For what? To find out what is the fuel consumption during cruise or loiter, right? So let us solve an example. We have been talking about so many formula, etc., etc. There is every chance you lose the focus. Let us come back to one application so that it goes to your mind. For example, this is station 1 to station 2, which I call a cruise. And let's say this is around 911,400 feet, which is roughly equal to 1500 nautical mile. I am writing this unit because most of the documents you will find, engineering documents in the shop floor will be in nautical miles. If it's a DGC regulations, nautical miles, and fit FPS system, you can always find an equivalent SI unit values. So this is the range. Range means, in this case, we are focusing that I want to compute the fuel consumption if the airplane is cruising from point 1 to point 2 for a range of this much of feet at a speed 0.6 Mach. Okay? So what is the fuel fraction? That is, question is what is W2 by W1. If I know this ratio, I know how much fuel is consumed, provided I know what is the weight at W1. Okay. So how do I do that? We are assuming we are talking about jet engine and high bypass ratio. This to, and speed is 0.6 Mach and range is 911,400 feet. How do I use whatever you have learned? So it's talking about range. So range for jet, I know it is V by C, L by D to Ln Wi minus 1 by Wi. That is W1 by W. This is, if I call it 1, they call it 2. If I reverse it, I get Wi by Wi minus 1 is equal to exponential minus R C V L by D. Once I want to apply this formula for a range, I need to ask ourselves a question, what is that L by D I should fly so that R is maximum? I'll again revisit that question, is what is that L by D I should fly at a given speed V so that the range is maximum? You know the answer already. We will come back when we actually solve this problem. We have talked about this. If you have forgotten, so let me remind you, we have seen for jet, for the part of cruise, I should fly at 0.866 L by D max, and if I am loitering, then I should fly at L by D max. This already I have addressed in earlier lecture. So now you know that if I want to know W2 by W1, I need to know the value of C, value of R is known, V is known, how much L by D I should fly, because it is range for jet, so L by D should be 0.866 L by D max. So I need to know what L by D max I will be flying. So I will be talking that in the next lecture, but today I am focusing more on C, how do we use this C, and you still remain unit by consistent to get a correct number. Because most of us commit mistake here, because most of us fail in handling C because the units are given in a very funny manner. Okay, that's why I am putting this time here. Okay, so now the value of CT for high bypass ratio turbofan, we have seen this value to be roughly 0.5 per hour. If you see any literature or any design handbook, even old edition of Raymer, the units are like this. New edition, yes, there are changes, but I am following an old edition. But we know that CT I have to convert into second because I am working in FPS. So this is equivalent to 0.0001389 per second, just divided by 3600. So now I am consistent. Although it is given per hour, I have to convert it into per second. I will be using FPS system of unit. So CT I have corrected, R I have taken in feet, so consistent. V is 0.6 Mach, so I write 0.6 into 3, what is that? Should I write 340 meter per second here? Will it be okay? No, this will be wrong because 0.6 Mach I have to work in FPS unit. So I have to write V equal to 0.6 into velocity of sound in FPS unit, and that is 994.8 feet per second. Okay, that is the speed of sound in FPS. So now everything I know, so I have to just put these numbers here. So now this W2 by W1 will be equal to exponential minus R means minus 911400000 into C. C we know it is 0.0001389 divided by V, that is 0.6 into 994.8 into L by D. L by D, you know, 0.866 into L by D max. Let us take L by D max as 16. We have not talked about how to select L by D. We will talk about selecting L by D max in the next class. For this computation, you take L by D max to be 16, and 15, 16, 17, these are typical values of L by D max for most of the airplane. What is important here, because it is the range part we are computing, and we have to ensure that for jet-driven engine, I need to fly at an L by D which is equal to 0.866 times L by D max. And if I do that, then I get W2 by W1 equal to 0.852. So from this ratio, if I know W1, I know during this leg how much fuel is consumed. Right? Similar exercise I can do it for loiter also. Only equivalently the numbers will change. Right? In the final example, we will be taking everything together, but it is better that piecewise we are very clear about the units As I repeatedly am telling, units are very inconsistent, right? Especially C and CT, etc. Right. Thank you very much.